Good morning, good afternoon, good evening to you all. The next session starts at 8:50 a.m. my time, 2:50 p.m. Vienna time, which is now. So I'm just going to ask Lucas to start the first video by Chiara, Piacentini, Hyunmin, Cheong, Mehran, Ebrahimi, and Adrian Butscher on multi-speed gearbox synthesis using global search and non-convex optimization.
Hello everyone, my name is Chiara Piacentini, and in today's presentation I'm going to talk about the paper Multi-Speed Gearbox Synthesis using Global and Non-Convex Optimization. This is joint work with my former colleagues at Autodesk Research, Hyunmin Cheong, Mehran Ebrahimi, and Adrian Butscher. In this presentation, I'm going to first give you an overview of the problem. We will then show you how we can decompose it into manageable subproblems and present 3 different ways which we can use to solve them. Finally, we will present some results. Gearbox synthesis is part of a wide class of problems known as configuration design problems, where we have as input a set of primitive components and some desired performance criteria. The goal is to find how to combine these components in such a way that we meet all the performance criteria and we maximize or minimize some objective. A gearbox is a mechanical system that transmits and converts an input speed to one or multiple output speeds by means of a series of rotating elements called shafts and gears. A power source rotates the input shaft with an input velocity, which in turn rotates the next connected shafts, propagating the speed throughout the gearbox and towards the output. Pairs of shafts are connected through gear pairs with different radii. The size of the gear's radii determines the speed change between the connected shafts. Typically, a gearbox is designed to convert the input speed into multiple output speeds according to several transmission ratio values. This is achieved by having multiple shafts and multiple gear pairs connecting the input and the output shafts. When a desired transmission ratio is selected, the necessary gear pairs are engaged by means of clutches. For the gearbox synthesis problem, the elementary components are gears and shafts. We are given as input a set of transmission ratios, and we want to find how to combine the gears and the shafts in order to obtain a gearbox that is able to achieve the desired transmission ratio values, while minimizing the total mass of the system. First, we can see how we can schematically represent the gearbox layout. The layout can be seen as an undirected multigraph where nodes are shafts and edges are gear pairs. 2 shafts are connected if there are touching gears, one placed onto the first shaft and the other placed onto the second shaft. In a gearbox, we always identify the input and the output shafts. Given a gearbox layout, we can identify several simple paths from the input to the output shaft, which will give different transmission ratio values according to this formula. Along with the schematic configuration presented in the previous slide, we need to find the details of each element in the layout graph. We represent shafts and gears as cylinders, defined by their position, radius, and length. The position is identified by the coordinates of the center of one of the circular faces of the cylinder. Obviously, we will need to maintain certain mechanical and geometrical constraints. The first one is that the transmission ratios need to be within a certain threshold from the desired target values, but we also need to maintain geometrical constraints such as requiring that all elements are within a box with specified dimensions, gear pairs need to touch, and gears and shafts do not collide. Let's see now how we can tackle this problem. The main idea is that we can break the problem into more manageable subproblems. We try different decomposition, but in this presentation we will focus only on the best performing one. This decomposition is based on the identification of 3 subproblems. We first generate the gearbox layout. This is the multigraph representing the connectivity between shafts and gears presented in an early slide. we require the graphs to have at least k distinct simple paths, where k is the number of transmission ratio that we want to achieve. Notice that while generating these graphs, we can exploit graph isomorphism to identify equivalent graphs. On the right, you can see some examples of different gearbox layouts with at least 4 paths. Once we have a layout graph with at least k paths, we need to associate each of these paths to one of the transmission ratios. Again, we can exploit some tricks to detect symmetric assignments. If you're interested, details can be found in the paper. Finally, once we have the layout and the path assignments, we can determine the parameters of each element in the gearbox. As mentioned before, the parameters are the position of shafts and gears, their length, and their radii. The mechanical and geometric constraint can be mathematically formulated as follows. We first require that the transmission ratio is within a threshold. All the elements are within the box. Gears in a gear pairs touch each other. And finally, we require that the elements do not overlap. Since we assume that shafts and gears are cylinders, we can express this constraint in this way for every pair of elements. As you can see here, the subproblem can be expressed as a non-linear, non-convex optimization problem, for which standard solvers can be used. This is how we decompose the problem, and for every subproblem, we try different algorithms, which we combine as shown in the rest of the presentation. The first approach we tried is simulated annealing, which we use to generate different layout graphs. Each state is a graph, which may or may not have k simple paths. We start with a randomly generated graph, and we randomly apply a transition that changes the topology of the gearbox. The possible transitions are adding or removing an edge between 2 existing nodes, adding or removing a node, or replacing one edge with another. If the generated state doesn't have k simple paths, the state is automatically discarded. Otherwise, it is evaluated by solving the 2 following subproblems: path assignments and parameter optimization. For path assignment, we randomly select n assignments, and for each of these, we run a nonlinear optimization solver, IPLOP. The minimum among the feasible solutions is the value of the state, which we keep or reject according to the temperature of the system following the standard simulated annealing procedure. The second approach is based on a complete search algorithm. We generate gearbox layout graphs using best first search. Again, a search state is a gearbox layout, and transitions modify the topology of the graph. We start from a layout where there are only the input and the output shafts. Given a state, we generate all the possible successors by adding a new gear pair in all possible ways between 2 existing shafts or between an existing shaft and a new one. Since we keep in memory all the states that we have encountered so far, we don't need to apply transitions that delete gear pairs. Every state is associated to a priority value, which decides which state to expand next. This priority value is either the solution of the path assignment and the parameter optimization problems, if the generated graph contains more than k simple paths, or it is an estimation on the number of gear pairs that we need to add to obtain k paths. In path assignments, we want to generate all the possible assignments and solve the parameters optimization for all of them. The final approach is based on an evolutionary algorithm called estimation of distribution algorithm, or EDA in short. We start with a population of individuals where each individual is a gearbox layout. With this method, we impose some additional constraints on the individuals. For example, we impose an upper bound on the number of paths contained in each graph. Each individual is evaluated by enumerating all possible path assignments and solving the parameter optimization problem for all of them. Once this process is completed for one generation, we select the best individuals, and we use them to calculate the probability distribution of the gear pairs in the graphs. Then we generate new individuals by selecting an edge with a probability given by these distributions, and incrementally add the selected edges starting from an empty graph until the desired number of simple paths is obtained. The process is repeated for several generations until a termination criteria is met. In our experimental evaluation, we compare these three approaches. We first compare simulated annealing and best pair search to verify the limits of a complete search algorithm against a stochastic method. As shown in the figure, for the small instances on the left, best pair search finds better quality solutions, but its performances deteriorate very quickly for the larger problem on the right. On a more challenging dataset, this behavior is even more evident, and we can see here how the best approach is EDA, which is able to consistently find better quality solution within the time limit imposed. The performances of EDA can be attributed to its ability to perform multiple evaluations in parallel. This concludes this presentation, in which we introduce the gearbox synthesis as one example of a configuration design problem. Please do not hesitate to contact us if you have any question. Thank you.
All right. Thanks for that presentation, Chiara. Let me see if there's any questions in the chat. If not, I have a couple questions. Good morning.
Hello.
The first one, I just wanted to double check in your experiment, you're minimizing the total weight, right?
Yes, exactly.
And so that's, I wasn't sure because you have a specific time limit, and that means that the exact method clearly was outperformed by the other methods within this time limit.
Yes.
I was wondering, in your simulated annealing approach, you have this decomposed structure where you have first the simple paths and then you continue the method. Is there anything that guides the simple paths? I assume that you do this multiple times, but is there any feedback mechanism to find different simple paths, for example, based on a Lagrangian penalty or of some sort?
In a simulating annealing, no. So we just use the objective that we find for feasible solutions to accept or reject
all right.
layout.
So that sounds good.
But yeah, it would be nice to add some feedback. I guess it will certainly improve the generation mechanism.
Sounds good. There are some questions here from David. When you solve the problem with IP-opt, how's the quality of the solutions? Could you perhaps use other global solvers like Biere or Skip?
So we couldn't actually use Skip because the work has been performed in a research institute, a private research institute. So we don't have like the academic license. So we only limit on iTalk, and the solutions were good. So there were some problems on the convergency of iTalk because the problem is nonlinear. So what we did to improve the performance was to first solve a relaxed version of the problem where we basically consider just the objective function without and the constraint on the ratio of the radius of the gears, and we discarded the constraints related to the collision geometry between gears pairs, and then we use this solution to seed the complete problem, basically, and that improve the convergence of iTalk.
All right. And so specific to this question, you were not able to use the commercial solvers to begin with also.
Yes.
There's a couple more questions. We have maybe 1 more minute. So Helmut Simonis asks, are the gears shared between the different ratios? I'm not exactly sure what he means. You probably are.
So basically, every gear pair can contribute to different transmission ratios. So
right, I think that's what he means.
Yeah.
And then one last question, I think it's a very good one as well. Were any solutions obtained by your method that were surprising to the domain experts? Could you outperform or improve the existing solutions?
Not really sure. Like we didn't check against a human species, so we don't know if the solutions were totally revolutionary or they were very plausible for a human designer. But it's definitely interesting to see how these approaches compare to a real human designer.
Mm-hmm. All right, thank you. And thank you for the presentation. Let's move on to the next one by Nicolas, Beldiceanu, Maria-Isabel, Restrepo-Ruiz, and Helmut, Simonis on parameterized bounds on the sum of variables in time series constraints. I think Lucas will start the video.
Welcome to this presentation on parameterized bounds on the sum of variables in time series constraints. I'm Helmut Simonis. I'm from the Insight Center for Data Analytics in Cork. This is joint work with Nicolas Beldiceanu and Maria-Isabel Restrepo from Nantes. We are looking at values that change over time given as an integer sequence. And that can be, for example, the output curve of a power plant, or the power consumption of a data center, or the manpower used per period in a scheduling problem. We are interested in the area under the curve, and that is equal to the sum of the values in the sequence. And that area under the curve describes the total energy use or the total manpower spent. So it's the typical objective in an optimization problem. We do this formally by defining time series constraints over a sequence of n integer variables, and they return an integer result variable r. And the components of that constraint are three things. There's a pattern sigma, which is a regular expression over the signature alphabet smaller, equal, and greater. There's a feature f and an aggregator g. Both are functions over integer sequences. Here we have an example. We have our time series here in blue with the individual values. We have the signature variables here, and we have two occurrences of a pattern increasing terrace and another increasing terrace here. This one has the width 2. For increasing terrace, we're only counting the points on the steady part. And this one has the width 3. So we have a feature value of 2 and 3 for the occurrences, and as aggregator we use sum, so we're getting 5 as the result variable r. The research question that we're interested in: can we bound both an lower and an upper bound the value of the area under the curve for these time series constraints? And can we do this generically, not for each constraint on its own, but for multiple constraints with a single mechanism, and possibly for families of constraints together? And can we make sure that these bounds are sharp and therefore as good as possible? And here we have an example. We are looking for size 14 problem, and we have 5 increasing terraces in there. We want to maximize the sum of these 14 variables. In the presentation, we will always try to look for the upper bound, so we want to maximize the value, and we have a domain from 2 to 6 for all the variables. If we ignore the terraces, if we ignore the constraint, we obviously have an upper bound of 84, 14 times 6. If we have the 5 terraces, then this solution here would actually show the sharp bound of 59. We can have here 2 terraces which are overlapping, and then 3 here. In between, we can reset the value, and we are trying to push these terraces as far as possible against the upper bound to maximize the bound that we can achieve. The contribution is we have a parameterized sharp lower and upper bound on the sum of the time series constraints for some 1 sigma and some with sigma families, where all x variables are in the same interval of a lower and upper bound. How do we do this? Well, we can't really go into details here. The main idea are we first look at the effects of a single occurrence of a pattern and the length of the pattern, and we are trying to push the pattern against the bound, the upper bound in our case, and we see how much space we lose because of the pattern on its own. And then if we have multiple pattern occurrences, we have to decide how they interact. If there are relatively few patterns, then we can space them out in our sequence so that there is no interaction. Otherwise, they actually overlap and therefore can influence each other. We also have to consider the effect of the domain size, and we are making the simplifying assumption that we have uniform domains. So formally, we do this by characterizing each time series constraint by some properties that we define, and then basically compute the bounds on the sum as a function of these properties. And we have a theorem that basically proves the correctness of the result. So here we just have 2 of the properties that we are looking for. Here we have for increasing terrace a single terrace. And so if we're pushing the single pattern against the upper bound U, we see that we are going to lose a little bit on our bound just because of that single pattern. In fact, the best we can achieve for a single occurrence is 4U minus 4, because we're losing 1 point here, 1 point here, and 2 points here. If the pattern is longer, we would lose more, and we can't push the pattern further up because of the constraints of our signature variables. And then here we have the situation where we have 2 patterns that overlap, and we see that they overlap in 2 variables, and in that overlap we are losing 2U minus 3 values, this one here and these 2 here. And again, we can't avoid that. So if we are forced to overlap the patterns, then we are going to lose progressively more of our bound that we can achieve. Here we have 3 examples of cases that can happen. Here we have a case of the number strictly decreasing sequence, and we have 3 occurrences here. And between each of the occurrences, we can reset the sequence to the upper bound, and therefore we're only losing the values of 1 for each of the patterns that occur. And for the remaining variables, we can just assume that we pick the upper value, the upper bound value. Here we have a similar situation, but for number peak. And we don't have to separate the peaks. We can have them in a single interval without a restart, because the pattern basically connects nicely. And then for the remaining variables, we can again choose the upper bound value. And here is the case that we studied before. We have 5 increasing terraces in a sequence of 14, and the only way of achieving that is to have only 1 restart, and therefore we're going to push the time series further and further down with the additional pattern occurrences, and therefore our bound will not be very, very high, and therefore it will be quite strong. How do we build this? Well, we have implemented all of this in our time series constraint package on 6's Prolog. We're testing this with synthetic results for time series between sizes 5 and 60. We try out all possible result values. That gives us altogether something like 45,000 runs. we minimize or maximize the sum of the time series variables. It's easy to see that the bounds basically work the same way for lower and upper bound. We tried two different search methods, one where we use a generic input order in-domain search for the decision variables, and one where we do this on the signature variables. We can also try and impose the minimal value of the cost value immediately at the beginning of the search. That will give us stronger propagation, and this works in this case because the bounds are strong. We have a baseline comparison where we only try and find the first feasible solution, and that obviously is a simpler problem. Overall, we have a timeout of 600 seconds, so we stop as soon as we reach that timeout. Here we see the results. We have our baseline for feasibility just here in purple, and here we have our best curve for the bounds. We see that without the bounds, we have these two cases here. The search method have only a minor impact. And these four variants basically then have different search methods and impose the cost bound upfront or not. We can see that the gap between finding the first feasible solution and finding the optimal solution is actually decreasing as the size increases. So we have an exponential speed up by using the bounds compared to the case without. An interesting implementation detail, the formula for the bound is actually quite complicated. If we try and impose that as an arithmetic constraint, this would be quite challenging. We actually pre-compute a table of the constraint between the different parameters and use that at runtime to get the strongest possible propagation at the lowest possible cost. So what we have done is we have added bounds on the total effort spent for the time series constraints. This is useful for many optimization applications that deal with time series constraints. For doing that, we defined and used some additional characteristics for time series constraints, and therefore get sharp lower and upper bounds for a single constraint. There are kind of two approaches that we could study in the future. One would be, at the moment, we are ignoring the interaction of multiple constraints over the same sequence, and this is something that we could look at in more detail. And then another extension would be to look at time variable weights on the variables. So instead of just having a simple sum of the variables, we would have a weighted sum. And obviously these are non-trivial extensions, but they might be future work.
Great. I don't know who is present to answer any questions, but thank you already for the presentation. Helmut, you're here with the same background even. Fantastic.
Yeah.
How are you? I think the major question I have, at least I think many others as well, is I'm sure, given your background, that you've looked at applications of this. Otherwise, you probably wouldn't have worked on this topic. Can you maybe share a little bit of the applications?
Yeah, so there are basically two problems that are very typical. One is a manpower planning where the area under the curve is the total manpower cost, and the time series constraint basically say how you can change the manpower from 1 week to another, say. And then you have for a year 52 variables, and that gives us roughly the size of the problem that we encounter here. And you want to minimize, obviously, the cost. The other problem is a power plant where you want to typically maximize the power output. And again, you have constraints on how you can operate this plant. And we did actually some experiments on our university power plant with this, where we actually have a CHP plant on campus, and we had control over that plant for a while. But the operators were not happy with us changing the output every time, going up and down. They had kind of very strict constraints how you can change the output curve and how often you can change that, and for how long you have to keep the situation stable. And that is the typical thing. You want to maximize the output, but you cannot change the output every half hour or every 15 minutes. You basically have to satisfy the rules, because otherwise you're creating more maintenance effort and more risk of a major breakdown of the plant, and that is not worth it, improving the efficiency of the system by a few percent if you then have €100,000 repair cost coming out of it.
Yeah,
so
understood.
These would be typical kind of situations where yes, you have a time series or a conjunction of time series constraints, but you're trying to minimize or maximize the total output or the total cost of the schedule that you're generating.
Mm-hmm. Thank you. Very, very interesting. If there's any other questions, this is your last call. This is my last call for questions in the chat. Otherwise, thank you very much, Helmut.
You're welcome.
And we'll move on to the next talk. That's by Katalin, Fazekas, Markus, Sinnl, Armin, Biere, Sophie, Parragh on duplex encoding of staircase at most one constraint for the anti-bandwidth problem.
Welcome everybody, my name is Katalin Fazekas and I am here to present our work on duplex encoding of staircase at most one constraints for the anti-bandwidth problem. This is a joint work together with Markus, Armin, Biere and Sophie, Parragh. And this long title already summarizes what I'm planning to talk about. I will start this presentation by first shortly introducing the anti-bandwidth problem, and then I will briefly describe our contribution, this so-called duplex encoding of some constraints. So let's define first the anti-bandwidth problem. This is a graph labeling max-min optimization problem where we are given a graph, for example here with 5 nodes, and we would like to assign numerical labels for each of the nodes of this graph in an optimal way. If we assign labels for the nodes, then for each edge we can calculate the difference between the labels of the connected nodes, and the smallest difference what we can find in the whole graph is the anti-bandwidth of the graph under the given labeling. So in this example labeling it would be 1. And our objective is to find such a labeling for a given graph that this anti-bandwidth is as high as possible. And this problem can capture different assignment and scheduling problems of real life, and previously there were already several heuristic and exact methods introduced to address them efficiently. The most recent related work was introduced by Markus, one of the authors of our paper, and in his approach the optimization problem is solved by answering a sequence of decision problems with the help of a mixed integer programming solver. So this is an iterative MIP formalization of the anti-bandwidth problem, and the question what we would like to answer whether we can construct a labeling for a given graph such that the anti-bandwidth is greater than a given value k. And if we can answer this question efficiently, then we can just always increase the value of k until we get a negative answer, and in that case we know that the last affirmative k value was the optimal anti-bandwidth. So to answer this question, first, for each node of the graph and for each possible label, a new Boolean variable is introduced such that this variable is true if and only if the given label is assigned for the given node. Using these Boolean variables, the decision problem can be formulated with the help of 3 sets of constraints. First of all, we have to guarantee that we find the labeling for our given graph by ensuring that each label is assigned to exactly one of the nodes and each node gets assigned exactly one of the labels. So we have 2 sets of exactly 1 constraints. And beyond that, we have a set of constraints to guarantee that the final anti-bandwidth value is greater than k by simply forbidding for neighboring nodes to take labels that would yield a smaller anti-bandwidth value. And this is ensured with a set of at most 1 constraints. So this is the formalization that was introduced and which was efficiently solved by MIP solvers in previous work, and this is the starting point for all our proposed solution method for the anti-bandwidth problem. In our approach, we would like to use a Boolean satisfiability solver instead of the MIP solver, and this allows us to slightly refine the previous formalization of the antibandwidth problem. So as a very first step, we applied some simple formula transformations on the at most one constraints of the problem and ended up in a formula where we conjoin at most one constraints with the disjunction of at most zero constraints. What is important to observe here in this refined formula that each of these smaller at most one and at most zero constraints have the exact same syntactical shape. And this shape of constraints is the focus of our contribution by providing a linear-sized representation of them in propositional logic. So let's take a closer look on these constraint sets. We call them staircase at most one and at most zero constraints, and they can be defined by the set of Boolean variables what they constrain and by a numerical value which determines the length of each of the constraints in the set. And all in all, this shape of constraints can be familiar for people with some constraint programming background because they are also referred as sequence at most one constraints. The easiest to understand what do they express is to see an example. So I prepared a small one here when we have 15 Boolean variables and we say that the length of the constraints is 5. In that setting, a set of staircase at most one constraint set means actually the conjunction of these 11 at most one constraints, where if we realign them such that the same variables are under each other, then we get this staircase shape, which explains why do we call them staircase constraint sets. Having such a set of constraints, the question what we actually would like to answer is whether we can find a truth assignment to the Boolean variables such that each of these at most one constraints are satisfied. This is clearly a Boolean satisfiability problem, which means that we could use current SAT solvers to answer it efficiently. And a naive way to do so would be just to consider your favorite at most one SAT encoding and apply it on each of the at most one constraints of the problem to get a propositional representation of it and to use the SAT solver. But taking a closer look on these constraints, we can see that they actually share lots of sub-expressions with each other, and it indicates that there might be a smaller representation if we do not consider the constraints independently from each other. And this is the basic idea behind our encoding, where we do not try to encode all of the constraints independently, but rather just pick some of them. More precisely, in this example, we pick only 3 of the 11 constraints, and encode only these ones, but in such a way that all the other constraints can be then later expressed by just combining the sub-expressions of these already encoded constraints. To find such an encoding, we first have to understand what kind of expressions are actually needed to describe the other constraints. So first, let's just assume that somehow we encoded or selected at most one constraints, and then for each of the other not selected constraints, we will apply some kind of decomposition. More precisely, for example, when we talk about the at most one constraint over the variables x4 till x8, we can split it up into 2, such that then we can talk about a sum of variables x4 and x5, which happens to be a sub-expression in the first encoded at most one constraint, and this is combined with a sum over x6, 7, and 8, which is a subsum in the second encoded at most one constraint. More precisely, this subsum is actually the prefix of the second constraint. Similarly, if we consider the at most one constraint over the sequence of variables from x8 till x12, we can decompose it such that we get a subsum of the third at most one constraint, more precisely a prefix of it, and this is combined with the sum of variables x8, x9, x10, which happens to be a suffix of the second encoded at most one constraint. So these two examples already hint a pattern that we will need a representation for these constraints such that we can access all the prefixes and all the suffixes of the exact same sums in them. And to do that, we will consider the variables in the sums first by a left associative grouping to generate the prefixes, and then a right associative grouping to generate the necessary suffixes. And so we encode them always twice. And because of this double effort, we call our encoding duplex. Beyond that, we can also see that these sub-sums are occurring not just in at most one constraints at the end, but also in at most zero settings. And because of that, we have to find an encoding where we can guarantee that these at most zero constraints are also present at the final representation. Our solution to these requirements was to use binary decision diagrams to encode our selected at most one constraints, and I will not go into the technical details of that. If you are interested, then please check out our paper. The only thing what I would like to show here is that using binary decision diagrams, we can express the variable groupings in our constraints just by the order. How do we decide on the truth value of the Boolean variables in it, and also these diagrams at the end contain all our necessary at most zero constraints as substructures. So if we build these BDDs in the correct way, then we can express after decomposition all our other not encoded constraints just by combining smaller constraints, which are all happen to be nodes in our built BDDs. So if we introduce Boolean variables to refer on each of the substructures of the built binary decision diagrams, we can describe all the other constraints just by combining the right Boolean variables with each other. So all in all, the main steps of our encoding are to select some of the constraints and construct two binary decision diagrams for each of them, and then express all the other constraints just by combining the right substructures of these built BDDs. Doing so, we gain a linear-sized encoding of a staircase at most one constraint set, which happens to be much smaller than any other off-the-shelf SAT solution, as this figure also shows it, where we have 500 Boolean variables, and we measure the number of clauses for each possible length of the constraints, and we can see that when the length is close to the half of the number of variables, all the other naive encodings become at least quadratic, while our encoding remains all the time linear. To demonstrate that our encoding is not just compact but can be solved efficiently, we evaluated it in the context of the Antibandwidth problem, where we provided a SAT-based iterative solution method and compared it to the state-of-the-art MIP approach, and also compared it to off-the-shelf constraint programming methods. For the evaluation, we used the Harvard-Boeing matrix collection, and here you can see first only the smaller instances with relatively a small amount of nodes and edges, and you can see that the different methods perform quite comparable, but for example our approach can identify an optimal antibandwidth value which cannot be found by any other method. And this difference between the approaches become more visible if we take a look on the larger instances where the naive solutions do not scale, and although the state-of-the-art can solve some of the instances, in most of these cases our approach has an improved performance, and here also we found an optimal value which was not found previously. So to sum it up, in our paper we introduced the linear-sized R-consistent SAT encoding for sequence at most one constraints, and based on this encoding we implemented an iterative SAT solution method for the antibandwidth problem, which improves the previous state-of-the-art. And in the future we would like to try a hybrid solution approach for that problem, and also we would like to generalize the idea of duplex encoding for arbitrary sequence at most constraints. So thank you very much for your attention.
Thank you very much. That's great. Good morning, good afternoon.
Hello.
If you have any questions, please post them in the chat. We do have time for some questions. I think it was a very interesting talk. I'm always intrigued by these kind of problems. There's BDDs here, the sequence constraints. Since you reference work from CP on sequence as well, you're probably familiar with the paper by Sebastian Brandt and others, Nina Naroditska and so forth, on different encodings of the sequence constraint. And I do think that what you have is very different from what I remember is in that paper. But can you please confirm that if you are familiar with that work?
Yes. So to be honest, when we were working on this paper, we were not aware of this line of work. So that's why it was really interesting to see when we found it. And yes, then we included a little comparison also to them. But I think our approach is significantly different because we did not find anywhere a hint on this that we can use a proper order for the BDDs if we work with BDDs, and also to split up the constraints and then try to combine pairs. And also what we found there, the smallest encoding was still slightly larger than our representation in the worst case.
Yes, I believe that's true indeed, yes. So I think it's very nice. I have here a question from Andras. How would at most K scale with the duplex encoding?
This is interesting. It would definitely not be any more linear because the decomposition rule would be different and there we would have some explosion. But I think the basic idea is really easy to generalize because with BDDs you can express also at most K and you would just have more layers. But we are still, so we don't have any results regarding how it would be compared to general sequence encodings.
But just from my own understanding, you don't necessarily think it's going to be exponential in K?
I don't know. I don't want to claim anything because I can't prove any.
No, sure.
I think there are some corner cases where it can be still really small. But I think it's definitely something which worth to try and see how large it will be. So we are working on it also.
Sounds good. Thank you very much for a great talk and
you.
great work. Let's go to the last presentation of this session by Özgür, Akgün, Nguyen, Dang, Ian Miguel, Andres Salomon, Patrick Spracklin, and Christopher Stone on discriminating instance generation from abstract specifications, a case study with CP and MIP.
Hi everyone, my name is Nguyen. This is a joint work with Özgür, Akgün, Ian Miguel, Andres Salomon, Patrick Spracklin, and Christopher Stone. We are all from the University of St. Andrews. In this work, we will present an automatic instance generation system that can produce instances with discriminating powers between two solvers. This work is based on an automatic instance generation system for CP that we proposed back in 2019. In this system, there are two inputs. The first one is a problem specification written in Essence, the constraint modeling language that supports high-level abstract types like sequence, set, partitions, or functions, and also nested types. The second input is a solver that is supported by our Essence CP toolchain. It can be a CP, a SAT, or an SMT solver. By combining the toolchain with the automatic algorithm configuration tool iRace, the system can automatically generate graded instances. We defined graded instances as valid instances. It means that they have to satisfy certain properties defined by the user in the problem specification. For example, consider the vehicle routing problem. We would want instances that have no customer demand that exceed the capacity of the vehicles. Another example is where the user can impose some constraints for the structure of the distance matrix between customers in order to make the generated instances more realistic. The second property required by the graded instances is that they have to be satisfiable. And the last one is that they have to be non-trivial for the given solver. In this work, we expand this system to support the generation of discriminated instances. Discriminated instances are the ones that exhibit a pronounced performance difference between solvers. They will be useful for the cases where we want to understand the strength and weakness of each solver, and they can also be applicable in the case where we want to do the training for a portfolio of solvers in order to make sure that the portfolio have a good performance coverage of the whole instance space of a given problem. In this work, we focus on a simplified situation where we only have two solvers. So we will be looking for instances where a favored solver performs significantly better than a based solver. And we demonstrate the work on a case study with the CP solver Jeff and the MIP solver Duplex. Now I will explain how the system works. In the first step, given a problem specification written in Essence, the software conjure, which is a component of our Essence tool change, will automatically create a parameterized instance generator for that problem. This instance generator is actually a CP decision problem in which we try to find a parameter setting of the original problem. So it means an instance of the original problem, given a range of the values for each parameter of that problem. Those range values will be tuned by the automatic configuration tool iRaise. Given a range proposed by iRaise, we will use the CP solver minion, which is also a part of our Essence tool change, to solve the generator problem in order to generate a valid instance that belongs to that range. After having a valid instance, we can evaluate that instance to see how discriminating it is, and we will use that information to give back to iRaise as a feedback, so that iRaise can use that information to improve the tuning. One issue is that currently our Essence tool change doesn't support MIP solvers, so here we use MiniZync to run Duplex. So the flow would be, we use our tool change to generate MiniZync input, and then we will use MiniZync to generate the input required by Duplex. This is how we design the score to find discriminating instances. First of all, we are not interested in the generator parameter configurations that are unset or unsolved because they don't give us any instance. We also penalize the unset and unsolved instances. Moreover, we are not interested in instances that are too easy for the base solver. We are also not interested in the instances that are too difficult for the favored solver, so we also penalize them. And the score is also designed in order to maximize the ratio between the solving time of the based solver and the favored solver. We demonstrate the system on 4 optimization problems. The first problem is the transshipment problem. This one can be formulated as a network flow problem, so we would expect Duplex to outperform Jeff on this problem. The second one is the progressive party problem. This one is a classical CP problem, and in literature it has been shown by experiments that CP works very well on this compared to various MIP formulations. So we expect Jeff to dominate Duplex on this problem. The third problem, warehouse location problem, and the fourth problem, capacitated vehicle routing problem, we don't have any prior knowledge on which solver will win. For each problem, we do 2 experiments. The first one, we have Jeff as the favored solver, and the second one, we have Duplex as the favored solver. We also impose a time limit of 5 minutes on the favored solver, and we are not interested in the two trivial instances for the base solver, so we give a minimum solving time of 10 seconds for the base solver. We also give a 25 minutes time limit for the base solver, so we know when to stop an evaluation of an instance. This is the experimental results. Here we plot the instances failed by the two experiments for each problem. The axes are the solving time of the corresponding solver on each instance. The green dots are instances generated by the just favor experiments, and the blue dots are the ones generated from the experiment where we have Duplex as the favored solver. The discriminating instances are the green dot below the diagonal line and the blue dots above the diagonal line. We can see that for progressive priority problem, the number of instances where just take less time to solve than Duplex is far more than the number of instances where Duplex win just. So this confirms our prior knowledge that just works generally better than Duplex on this classical CP problem. Interestingly, for CVRP, we also observe the same kind of behavior where just also dominates Duplex. For the transshipment problem, we find no instances where just wins Duplex and a lot of instances where Duplex take less time to solve than just. This also confirms our knowledge that for this transshipment problem, Duplex dominates just because it can be formulated, because the problem can be formulated as a network flow problem. For the warehouse location problem, we also see the same kind of behavior where Duplex dominates just, and this is also an interesting and new knowledge that we only know when we do this experiment. For the first two problems, where we do find discriminating instances for both solvers, we also do some feature analysis on the generated instances. So the aim of this analysis is to see if there is any important features that can determine which solver will win. We use the 95 flat-zinc features given by the mini-zinc 2-fit tool, and we build a binary classifier for each problem, and then we plot the top 10 most important features using the mean decrease impurity measurement. For progressive priority problem, we saw that there is one feature that seems to be more important than the rest. This can be interesting information for the developers of the two solvers in order to get more insights into the solving behavior of their solvers. For CVRP problem, the first 8 features seem to be equally important, and in this case, it would be more difficult to get any useful insights. In conclusion, in this work, we have provided an automated instance generation system for creating discriminating instances between two solvers. There are several things we would like to continue working on. The first thing is that we want to expand the system to generate discriminating instances for more than two solvers. The second thing is to improve the feature analysis part. The third thing is about improving the diversity of the generated instances by integrating some diversity mechanism into the tuning of arrays. And the last thing is to investigate the applicability of our system in building portfolios of solvers.
Thank you very much. I hope we have a representative. Hello, Nguyen. How are you? Very nice work. if anyone has a question, please put it in the chat. Let me start with one question. I think the connection to algorithm portfolios is an obvious one and a very good one. Now, there is a distinction between portfolios. There's several distinctions, but one of them is, for example, model-specific or instance-specific portfolio design. And in your case, it looks like the features that you extract for these problems are basically model-specific or structurally part of the problem rather than instance-specific. Have you thought about making these instance-specific? And I'm asking the question because you're really spending a lot of time generating instances to begin with. And you could then, when you do that, also perhaps design an experiment that you impose specific features for this purpose.
Yes, thank you. This is a great question.
I cannot hear you. I don't know why. It's very... Yeah, if you put it right in front of your mouth, I think it's even better. So very close to the microphone, please. Yeah, now it works. Thank you.
I'm sorry. So thank you. This is a great question. Actually, the current features, they combine the properties of both model and the instances. So because the flat-zinc features, they are created by through the pipeline. So they would combine the essence model specification and the parameters of the instances into one single input for each solver. So it would represent both information. But as you say, it would be interesting to, because this one is model specific in the sense that it depends on the chosen encoding and reformulation. So that's why we wanted to improve the feature analysis. One way to look at it is to develop high-level features on the essence level, because hopefully we can extract the structural information in that way, because when we represent a problem in essence level, then we can see the structure like a matrix or a set of sets or a set of partitions. So yeah,
I see.
That is future work.
Yeah, thank you. Thank you. One last question by Matteo. Let me see here. When considering the distinct discriminating features, are you taking into account the solving times? I think he meant the idea here is that the instances that solve in less than 1 second or instances that take considerably longer, they have a different role, I guess, in should have a different role perhaps in your evaluation regarding the features. But I think based on what you just said, I don't think that you have that is, I mean, I would consider this probably future work as well, because I don't think you spend too much time on that feature analysis.
Well, yeah, I mean, when we generate the instances, yes, we do consider the solving time into the evaluation of the quality of an instance. So we use solving time to see how discriminate the instances between the two solvers. I'm not sure if that is if that answers the question, or if
I'm not sure either. But I think it does, because Matteo says yes, thanks. That's great.
Okay, thank you. I'm glad.
All right, in the interest of time, thank you very much, man. And this concludes the session.